Assalamualaikum. Good morning. Hello. Assalamualaikum. Good morning. Hello.
Morning,
Waalaikumsalam,
Doctor.
morning.
Good morning.
Malam.
Okay. Don't sleep, huh? Okay. We move to the slide number 68. Okay. PD controller. After last week, we discussed on the P controller and PI controller. Okay. So P controller have the disadvantage that is steady state error exists along the way, even though we increase the gain from 1, 10, 100, and so on. Then the existing steady state error has been uh, solved by PI controller, where PI controller responsible is to improve the steady state error from finite value to 0. Okay. Because we increase the system type, okay, from type 0 to type 1. And yet, when we reduce the steady state error, it takes a long time, okay? From the previous examples, it took about 500 to 600 seconds in order to achieve zero steady state error. That is too long, about 10 minutes, okay? So that's why we propose the third controller, which is known as proportional and derivative PD controller, okay, as shown in the slide number 68, okay, where we, sorry, 67, sorry, 67, where we use PD controller to improve the transient response, meaning that to make the system faster from slower, and then maintaining the steady state error at 0, okay, and as small as possible. This transient response can be improved from slower to faster by adding a single zero to the forward path. Okay, this one. Okay, of the feedback control system. So this zero can be represented as GPD, transfer function of a PD controller, equal to KP plus KDS. Okay, which is equal to KD multiplied by S plus KP KD. Okay, meaning that we add one zeros at the whole transfer function. Okay, and the zeros value here is the ratio between the KP and KD. The gain of the P controller and the gain of the derivative controller is the ratio KP plus KD, and is known as Z. Okay, zeros, KP plus KD. So we can simplify it become K S plus Z, where K is the gain of the PD controller and Z is the zeros value, okay, of the PD controller, where this zeros value is a ratio between gain KP over gain KD. So that's why for PD controller, we must have a proper selection, proper calculations to locate the zeros value on the S-plane, okay, in order to improve the system transient response. So we look into these examples, uncompensated system here. So what is the open loop transfer function here at uncompensated system? What is the open loop transfer function? Akmal Hakimi? Tak datang.
Apa ni,
K
S plus 1, S plus 2, S plus 1, lepas tu bracket S plus 2, S plus 5, S plus 6.
Okay. So tiga sajalah. S plus 5 tak ada. S plus 1, S plus 2 and S plus 6 for this diagram, for E. Uncompensated. Uncompensated tu meaning before PD controller design. Okay. Before controller design. And then we introduce the zero, which is Kp over Kd minus 2. Okay, so what happened is the zeros minus 2 will cancel the poles at minus 2. Okay, so when it cancel, the system becomes second order. So this one is the third order. This one cancel between 0 and minus 2. Okay, so it cancel out. So it becomes second order. Okay, you can see that the behavior of the system is second order instead of third order because we introduce 0 and minus 2. And then we change from minus 2 to minus 4. And now the system is become third order again. Okay, third order with 1, 0 and minus 4. And finally, we introduce 0 and minus 3. And this one still third order system with 0 and minus 3. But the shape of the roller coaster has been changed from uncompensated to second order to third order, and the second one, third order, which is at minus 3. You can see the curve there. When you see 0, so it is curvy at the real axis. Okay. So all compensated system operates at a damping ratio 0.4 as the compensated system at 0.4, which is here. Okay, so 0.4, what is the angle of theta? Irfan Hakimi, what is angle of theta for damping ratio line 0.4?
66.42.
66 point.
42.
Okay, so this is the line of theta. Okay, which is 66.42. For all the compensated system, the closed loop system have more negative real and larger imaginary part as compared to the uncompensated system. So thus, the compensated system operate with the shorter settling time and peak time. Okay, so the settling time short and the peak time also short. Okay, short meaning very fast lah. Okay, so this system B give the best transfer response, which is this one, because it's a second order system. Okay. In summary, adding a 0 on the forward path improve the transfer response as well. So we need a proper selection. You have to calculate what is the suitable zeros value of the PD controller. Okay. By simulations, you can see that the first one, the uncompensated system, okay, is shown in this black response. The input is 1, guys. Input is 1 volt. Step. Okay. And then the output for the uncompensated system produce error. Okay. Big error. And then we introduce 0 at -2, 0 at -3, 0 at -4. So 0 at -2 is a second order system. Okay. But 0 at -3 and -4 is the third order system. Okay. So which one is the best one? The faster one from the graph? 0 at -2, 0 at -3, 0 at -4, or the uncompensated system? Which one is the fast response? Gun, Wilik.
0 at -2.
0 at -2, eh? This one, fastest one, which is near to the y-axis. Okay, below, this is 1.5. I think it's about below 1 second. Okay, below 1 seconds. So example 4, given the system, design a PD controller to yield a 60% overshoot. Okay, with a threefold reduction in the settling time. Okay, check the design using MATLAB. Okay, so for this figure, you need a graph. Okay, you need a graph. I share you the graph. Did I share you the graph of the, what do you call that? Overshoot versus zeta. Hello guys, did I share you the graph? Hello?
Zero.
No. Okay, I share you the graph. Refer to the WhatsApp. Muhammad Haikal, refer to your WhatsApp.
Yes, doctor.
At 16% overshoot, what is the corresponding zeta value? This graph, the one that I shared in the WhatsApp with the scale.
About 0.5.
0.5 apa? Because from my whiteboard, 0.5 something. I want to know the exact value.
0.504.
16 eh. 12, 12, 14, 16, 18, 16. 16 is 0.52. Pi 1. Berapa? 0.504 eh?
Yeah.
0.504. Okay. And then with the threefold reduction in settling time. So what do you mean by threefold reduction? So this sentence must be understood, meaning that the settling time new is 1/3 settling time old. Okay. Yes. Okay, guys. Can? That is the meaning of a word of threefold reduction in the settling time. Check again, design using MATLAB. So this is the given transfer function. So as you know that you already know what is the shape of it. Okay. 0, -4, -6. Then the green one, Okay, something like this. And towards infinity. Okay. With the open loop poles is 0, -4, -6. Okay. Alif. 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 Ada.
Saya doktor.
What is the system order in this case? For example,
Third order doktor.
third order. One more question. What is the system type? Alif. System type.
Zero type doktor.
Salah tu. I'm afraid the answer is wrong.
First kena.
Tengok dia punya depan bawah tu apa. Alif.
First kena.
Oh, first type doktor. Oh.
First type. System type 1. Bukan first type. First order system type 1. Okay. So as for 16% overshoot, you use graph. Okay. Do not use formula. So it will make you slower. Okay. No need to use this. No need to use this. Just use this one. Okay. Everybody can understand? Graph is given as shown in the WhatsApp list. Okay. So this is the zeta. What is the theta just now? What is the theta just now? Oh, theta tak tahu eh. What is theta? Junlog.
Yes.
What is the value of theta?
59.74 degree.
59.74 degree. Okay, so it locate here, the line, and then it intersect with the root locus. Okay. At the dominant pole. As shown, what is the dominant pole value? Yiking. What is the dominant pole value? Yiking. Tak tahu. Mazin, what is the dominant pole value? Absent. Chong Mu Chuan. Chong Mu Chuan.
Negative 1.2 plus J 2.07.
Okay. What is the gain value at dominant pole? Sharon Lau.
43.5.
43.5. And then Muhammad Iqmal Daniel.
Yes,
Muhammad,
doctor.
what is the third pole value?
The value negative 7.6.
How you get it? How you get the third pole value? Using what?
Formula.
I know the formula. What is the name of the equation?
Characteristic equation.
Characteristic
Equation.
equation with the gain value 43 point. 43 point.
0.7.
0.5.
0.5. Sorry.
Daniel. Daniel. Oh, Daniel. 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 Marina Jocelyn. Marina Jocelyn.
Yeah.
What is the characteristic equation? for the system?
The S times with S plus 4 and S plus 6.
Plus?
Yeah, S times with S plus 4 and S plus 6.
Not enough.
Plus K.
Plus K. Not enough. Equal to? Equal to?
0.
Okay, equal to 0. Thank you. So you must understand this slide number 73. Okay, you must know how to calculate each value of the data stated in the slide number 73. So from the root locus, you get zeta 0.504 using graph. Then include the dominant poles. Okay. And then this is where it come from, the old settling time, which is 3.32 seconds. How do I get it? From the formula 4 divided by real. What is the real part of dominant pole, which is minus 1.204 magnitude, positive. So 4 divided by 1.204, you get 3.32 seconds. This is the old settling time. What is the peak time? Pi bagi omega d. What is omega d? Omega d is the imaginary part of the dominant poles, which is this one, magnitude. So 1.52 seconds. So you can write it here, pi over real. Okay. And then calculate the kV. Why we use kV? Why we use kV? King Ying Tan. Why we use kV? Why not kp?
Because it is type 1 system.
Okay, because it's a type 1. And the formula for kV is limit s to 0 SGS. Okay. So you use the formula GS, which is K over S plus 4, S plus 6. And this one will cancel out. Okay. So what left is K is 43.35 from the locus previous drawing. And then divide by 24. 6 multiplied by 4. So the kV is equal to 1.8. So this kV will go to the steady state error formula for system type 1, which is 1 over kV. 1 divided by kV, which is the error is 0.55. Okay. So this is the plot. Okay. This is your theta. Okay. So the length between 0 to dominant poles here okay, Yong Seng,
Yes.
the length between 0 to dominant pole is known as
Then natural frequency
omega n.
omega n.
What is the value of omega n? 2.39 radian second. Right. So from there, from the 60% overshoot, the closed loop can be found at here, 3.32 second and 1.52 second. Though this is the old value. Okay. Old. So the steady state error is 0.55 by using the K value 43.5. So the third pole is minus 7.59. Thus is the second order approximation is valid. Okay. Why second order approximation is valid? Why? Shaishin, why second order approximation is valid? Hmm? Why? Why? Shaishin? Oh, Shaishin.
Like imaginary axis.
Hmm? What is the dominant pole? Minus. What is the dominant pole here? Minus 1.205, am I right? And the imaginary? 2.064. Third pole? Shaishin?
Negative 7.59.
Negative 7.59. So, why is it valid? Calculate the ratio. Shaishin?
6.299.
6.299. Okay. So if negative 7.59 second order approximation is valid, I think this is not valid. Is not valid. Okay, because it's greater than is greater than 6.29, which is greater than 5 kan. Yang kita belajar. Below 5, second order approximation. Okay, betul. It's greater than 5, sorry. It's greater than 5, so the approximation second order is valid because it's greater than 5. Sorry, this one. So you have to put notation here. Okay. Due to ratio greater than 5. Okay. Everyone understand? Understand, So the desired the desired specification is we want to maintain 60% overshoot. And at the same time, we want to make the settling time shorter. Okay. Which is 1.107. Okay. How do I get 1.107? The old settling time 3.32 divided by 3. Okay. So this one will become the new settling time. So therefore, the desired closed loop calculation now has been changed. Okay, because this one, okay, is T as new is equal to 4 divided by real. Am I right, guys? Hello, guys. Hello, guys.
Yes, okay.
Good.
Okay, 1.107 is the new settling time. Divide by 4 real. So what is the new real? 4 divide by 1.107. Berapa?
3.61.
3 point.
613.
This is the new real. That's why you dapat minus 3.61 there. Okay? That's why 3.61 you get there. Okay? And for this, after you get 3.61, which is over here somehow. Okay? So you go to the locus. Okay? So at the zeta line, so you will get the imaginary value automatically. Okay? So the line of 3 minus 3.61 straight here, straight, cut the zeta 0.504, then turn right, so you will get the 6.193, the new imaginary value. Okay? So this is the calculations there. Okay, so we got the omega n, new omega n, or you can use either graph or you can use using omega n. Once you get the new zeta, the new real, okay, the new real, which is 3.61, then you use the omega n formula, okay, which is omega n is equal to 4 divided by 1.107 multiplied by 0.54. This formula come from T as new 4 divided by real kan. So real is zeta omega n. Okay, so zeta fixed. That's why omega n is 4 divided by Ts new multiplied by zeta. Okay, so where you get 7.17 radian per second. Then you just multiply. You insert omega n here, you insert zeta here, so you get the new closed loop poles, which is 6.193. So this is the new poles, the new dominant poles. The new dominant poles, okay, to achieve 3-4 reduction settling time. So once you get the new dominant poles here, you plot on the graph or piece of paper as the test point, and then you make a straight line from -6 to the new dominant pole, -4 to the new dominant pole, 0 to new dominant pole, and then you locate -z anywhere on the real axis. So for this case, I locate here. You can locate here, you can locate here, you can locate over here, no matter. Okay, sir? As long as it's on the real axis. Okay, we assume -z is over on the real axis. Then we label the angle. Okay, we label the angle theta 2 for -6, theta 3 for -4, theta 4 for -z, and theta 1 for 0. Okay, by using the angle criteria. Okay, theta 1 plus theta 2 plus theta 3 minus theta 4. Why minus? Because this is the sum of angle due to zeros. This one is theta 1 to 3 is the sum of angle due to poles, equal 180. Calculate theta 1, okay, using trigonometry. Calculate theta 2, then calculate theta 3. Insert minus theta 4 unknown, then equal to 180, then theta 4, we get it as a 95.6, which is, makes sense. Our assumption is over here, okay, 95.6. Is over 90 degrees. So from there, from 95.6, we assume that this one is 95.6 degrees. So what is alpha? What is alpha? Wenhui, what is alpha?
Yes, doctor.
What is alpha, Wenhui?
Uh, 84.4.
How you get it?
180 minus 95.6.
Equal to
84.4.
84. Okay, which is here, and this is 90 degrees. Okay, so the length of this is 6.193. Okay, and then x is unknown. Okay, x is unknown. The length between the zeros to 3.613. So you use this tangent formula. Tangent 84.4 equal to 6.193 divided by x. The length between zeros to minus 3.6. Okay. Then simplify x. X is 0.607. So 3.613 plus 0.607. So this point is known as minus 3. Okay. The zeros is at minus 3, guys. So from there, so GPD is equal to KS plus 3. Okay. So we calculate the K, so we get 47.45. Okay. 47.45. And S plus 4, S plus 6, and S is the origin transfer function. So this one is we cascaded each other, meaning that we multiply. Okay, we multiply each other. Right, so from there, this is the damping ratio line. Zeta 0. What was it? 54. 504. Okay, so it's over there. And the root locus has been changed shape since there is a 0 at minus 3. Okay, so this is the origin, this is the minus 4 poles, and this is the minus 6. Okay, so as a result, when we introduce the PD controller, the uncompensated is here, which is the settling time was, what was it? The settling time 3.32, am I right? Hello? 3.32, TS whole 3.32 second. Now the settling time has been reduced 3 times, 3-4 reduction, so it will be 1.107. Yeah, TS new 1.107. Ahmad Syafiq. Ahmad Syafiq.
Doctor. Hello. Doctor.
3.32 second divided by 1.107. How much?
Uh, 3.102. 3.103.
3.1.
Wait. Sekejap, salah kira. 2.999.
Huh?
2.999.
2.999.
Yes.
So 3 lah. So meaning that
Yes.
the settling time has been reduced 3 times. Am I right? Am I right?
Yes.
Has been shortened 3 times. Okay, dipendekkan. So this is the PD controller transfer function, Kp plus Kds, which is Kds plus Kp over Kd. So Kp over Kd is 3. Okay, but Kd from the Calculation 47.45. Therefore, Kp is equal to 3 multiplied by Kd. Am I right? 3 multiplied by 47.45, which is equal to 142.35. Okay. So this is how we get Kp value and Kd value. This value will be inserted inside the hardware, either digital controller or analog controller. So this is how we calculate the controller. Okay, so this is before design, which is 3.47 settling time old. And after compensation, we get 1.15. Okay, so the ratio is about 3.47, 1.15. Akmal Hakimi, kira balik. 3.47 multiplied by 1.15. This one is after design. After
Bahagi ke darab, Doktor?
bahagi 3.45 divided by 1.15. This
Uh,
would be
3.0174.
3 point.
01740.
Okay. 3 point lah. 3 times reduction. To prove. Proven. 3 times reduction. Or 3-4 reductions. Any questions?
Tak ada tu.
Ada. Pak Izin, any question?
No question, Doctor.
Amir Farhan, any question?
Betul.
Ya.
Soalan test nanti macam ni ke rupa dia?
Ya, macam ni.
Oh, okey. Dia lagi straightforward ke lagi pening-pening sikit?
Can you in English because we have Arab brothers in the class.
Is it more confusing or it is straightforward question?
In between.
Oh, okay.
In between. Izzah Shamimi, do you understand?
Yes, Doctor.
Okay. So you understand, go to the example 5, guys. Slide number 84 before we break. Izzah Shamimi, can you read for me the questions?
Example 5. For a unity feedback system with open loop transfer function GS equals to 50 over S times S plus 5. A. Determine percentage overshoot and settling time of the system. B. Design a controller to have 50% reduction in the OS and 4-fold improvement in the settling time.
Okay.
Closed loop
Apa ya?
transfer function. Oh, that. Okay.
Munib. Munib, bye.
Yes, Doctor.
What is the gain value of the transfer function?
For this question,
Yes.
50.
Okay. What is the open loop poles value?
-5 and 0.
Yeah. Shukran, Habibi.
Afwan.
Shabik. Shabik Kashfi.
Ya, Doctor.
كيف حالك؟ كيف حالك؟ شبيك.
Ya, Doktor.
Yeah, what is the system order?
System. Second order.
What is the system type?
Type 0.
Type
1, type 1.
That one. Okay. So this is the closed loop transfer function where the characteristic equation is, what is the characteristic equation? Amir Farhan? Amir Farhan? Datang? Datang je. Amirul Afiq, what is the characteristic equation?
S square plus 5s plus 50, Doktor.
Tak cukup. Not completed. Aina, what is the characteristic equation?
S square plus 5s plus 50 equal to 0.
Okay, very good. So this is a second order system. So we compare with the second order transfer function omega n square s square plus 2 zeta omega n s plus omega n square that you learned in the previous control subject. So from here, what is the omega n value? Vian?
Yes, Doctor.
What is the omega n value on damped natural frequency?
7.0710.
What is the zeta value, Vian?
0.3535.
Okay, 0.356. So do we need to draw the locus of the system without controller? Can we find the specification needed? Yes, it can be yes, it can be no. Okay. So if we plot, it will be like this. Okay. Poles at zeros and -5. And then we draw the zeta line as Vian said. And the theta is 69.14. Okay. Hairan. 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 Danish Qayyim. Danish Qayyim. Danish Qayyim.
Yes, Doctor.
How you get theta? 69.4?
Cos cos zeta.
Okay. 69.14. Then draw, so we find the dominant poles. Okay. So we already calculate the omega n, 7.07 radian per second, zeta 0.356. And given the overshoot is 50% reduction in the overshoot and fourfold improvement. How you get 50% reductions? What is the original operating OS? We calculate zeta 3.56, am I right? EX5. Zeta 0. Over there? 356. Vian? Oh, Vian.
Yes, Doctor.
Can you help me to find the overshoot from the graph? At,
Overshoot,
at 0.356.
overshoot from the 0.2.
Yeah,
30.2%.
from the graph,
30.5%.
from the graph kan?
Mm.
So 0.356 is here. What is the overshoot? The corresponding overshoot over here? Hmm?
Wait, yeah.
Use the graph that I give in the WhatsApp.
Yeah. Around
30.45?
mm,
30.45%, eh? Okay.
30.45. Yeah.
30.45%. So this is the original. Okay, before compensated, before controller design. Our target is 50% reduction of overshoot. Am I right? So therefore 30.45% divided by 2. Izzah berapa? 30.45%.
15.23%.
2, 3. So this is
3%.
our target, our new target. And this new target, Izzah, will give you what zeta value from the graph that I give to you.
Zero 0.513.
Thank you. 0.153, okay? So this is what we are talking about, okay? Desired spec is 15.23 and settling time is 0.4 second. But we need to calculate the settling time as well because the settling time asks for the fourfold improvement in the settling time. So what is the old settling time? 4 divided by real, which is 4 divided by the what do you call it? The imaginary, the real part of the dominant pole, which is 2.5. All right, 2.5. Aina, berapa ni? Aina, help me. 4 divided by 2.5.
1.6.
1.6 second. Okay, 1.6 second. Okay, 1.6 second. Okay. So the new one will be fourfold, meaning that TS new is 1.6 second divided by 4. Aina berapa? 1.6 divided by 4 divided by 4.
0.4.
0.4 second. That's why you get 0.4 second over here. Okay, and from there you calculate the new real part, which is this one, meaning that you calculate the new omega n, which is 19.94. Then insert all the values, new zeta maintain, new omega n. Okay, so you will get minus 10 and plus minus j 16.73. So this is the new dominant pole. In PD, we must calculate the new dominant poles based on the spec given in the overshoot percentage, in the settling time reduction, in the peak time reductions. And then we use this new dominant pole. Okay, then we calculate the angle, okay, of theta 1 poles at 0, theta 2, poles at -5, and we put Z, we locate Z, we assume here, assume as theta 3. Then we calculate the angle for theta 1, theta 2, and theta 3. Theta 1 is 120 degrees, alpha 2 corresponding to theta 2, okay, is 73.36. Theta 2 is 180, 106.64. And then the theta 3 for the 0 for PD controller is at 47.51 here. Okay, then we calculate using the triangle. This is your theta 3, 47.53, 51, sorry. Okay, so this is 16.73, the height, and the distance between zeros and -10. The real part of the dominant pole is assumed as x. Calculate x. X is 15.32. So the distance of minus z is at 25.32. Okay, so this is the new zeros. Okay, the new zeros minus 25.32. Okay, then you calculate the gain k. Okay, the gain k can be calculated and you get 15. Either using trigonometry or using the gain formula, which is S plus 5, S plus 25.32. Okay, so you get 15. Then the GPD can be calculated as before, where the ratio is 25.29. Okay, and KD is equal to 0.3. Okay, and this is the complete PD controller with the transfer function. So when we redraw, we include the zeros here, minus 25. So we will give you a round circle of the new root locus. So this one is not important. There is no redraw for the root locus. Only we want to see the settling time. Previously it was 1.55 second, T as old. And after is 0.385, T as new. So what is the reductions? Franklin, what is the reduction?
Doctor,
1.55 divided by 0.385.
what 4.0259.
So has been reduced 4 times, 4 reductions. Okay, so we stop here. So we have a break about 15 minutes. Okay, 15 minutes break. Rehat sekejap. Boleh? Boleh rehat sekejap? Rehat sekejap. Okay, guys, we continue. Now we make revisions of the past year test one. Okay, we already did this one. Okay. So we move to the second questions. This one. Shazwina, are you there? Shazwina, are you there? Farina, can you read the question, please? Farina?
Okay. A robot arm system with a unity feedback loop has the root locus as shown in figure Q2. Initially, the uncompensated system is using proportional controller K and operated at damping ratio of 0.45. A. Determine the dominant poles of the uncompensated system and obtain its open loop transfer function GS based on the root locus in figure Q2. B. Calculate the steady state error of the uncompensated system for a unit step input. C. A proportional integral PI controller will be designed to improve the steady state error. Given the PI controller as below, GPI equals to Ks plus 0.01 over S. Number 1. Form the transfer function of GS times GPI and determine the value of gain K. Number 2. Compute the steady state error for the compensated system with PI controller. Compare the results to the answer in question 2b and provide a brief explanation in the improvement. Number 3. Determine the value of KP and KI parameters of the design PI controller.
Okay, thank you very much. So this is the given plot. Okay, proportional K and operated at 0.45. Okay, so 0.45 real zeta. Okay, so theta is equal to Amar. Muhammad Amar.
Yes, doktor.
Theta berapa?
Uh, 63.26.
Thank you. Soalan pertama, determine the dominant pole pada system. It is open loop transfer function and its open loop transfer function GS based on the rule locus. Okay. So this is the rule locus. Okay, given. Okay. So what is the open loop? Haikal. Haikal. Open loop transfer function. Ada.
Doktor, dia pergi tandas, doktor.
Kita anda. Okay. Muhammad Haikal. Muhammad Haikal.
Yes, doctor.
Open loop transfer function, please.
Uh, mm, K. Ni kan.
Okay. Ada
K.
open loop zeros not available. So K.
K over S plus 2. Oh, S plus 2. S plus minus J2.
Cakap betul.
S plus 2 minus J2.
Lagi.
Uh,
which is k over s plus 7, s plus 2, s plus 2 plus j2 multiply s plus 2 minus j2 because the open loop poles is what? What is the open loop poles? Muhammad Haikal?
-7 and -2 plus minus J2.
Then you masuk dalam transfer function s here. Then you multiply. You multiply dapat berapa? You multiply this. S plus 7, S plus 2 plus J2 berapa?
Uh,
S square plus 4S plus 8. Okay. Dan you multiply dapat berapa lagi? Junlog.
Eight.
Junlog. Junlog.
Yes, yes.
Multiply. Right. Betul tak? Hello? Betul?
Yes, yes, correct.
Alright. So now theta is what? 63.26. So I don't have the protector. Somebody have a protector, please give the associate values over there. Okay, something like that. Do you have a ruler? Okay, so I'm using my ruler. Can you see my ruler, guys? Hello? Can you see my ruler?
Yes, doctor.
Yes.
Yes, doctor.
So what I did is I draw a straight line on the iPad. Okay, so that is your zeta 0.45. And what is the dominant pole over there? Yong? Yong?
Yes, doctor.
Dominant pole over there? Minus D3. Okay? Voilà, Yong.
Negative 1.5 plus J3 tu.
Okay. Okay, done. Done, eh? So we need to calculate the gain K because we want to measure the steady state error. Can. So this is the transfer function. So system order, system type. E 非常 E 非常
Yes, doctor.
System order.
System order, third order,
System
and
type.
type 0.
So this one we use K, P, K, V, K, A.
K, 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 KP, KD.
KP, KV, KA. Or
KP, KP,
KK.
KP.
KP.
Yes.
Use KP. Do not use KK. KK is Kota Kinabalu. Kan? Hello?
Yes. Yes,
Hello?
doctor.
Yeah. So we have to calculate the gain K. How you calculate gain K at dominant poles? Aina Shakira? Aina,
Using magnitude formula,
that is
uh, S plus 7 multiplied by S square plus 4S plus 8.
which is equal to? Which is equal to?
Sekejap nak kira sekejap.
Tak payah kira. Congak je.
36.1.
Masya Allah. 36.1. So from there, you can calculate the KP. Kan? Limit S to 0. Kan? KGS. K 36.1 multiplied by S plus 7 S square for S plus 8 equal to Aina. Aina Shakira. Zero point.
0.645.
Okay. Then the steady state error. Aina.
0.608. 01 okay.
Panjangnya. Okay. So steady state error done. Kan? Okay guys, so far okay? Masuk exam ni?
Okay.
Tak?
Okey, okey.
Tak? Boleh ke tak?
Boleh.
Boleh.
Good.
PI controller.
Doctor, how to find dominant pool again? Sorry.
How to find dominant pole from the graph given, brother? What's your name, brother?
Ahmad Yusuf.
Huh?
Ahmad Yusuf.
Ahmad Yusuf. From the
Yes.
graph given, figure Q2, use your protector to draw the theta. Theta is 63.26. Okay, draw the theta. Then straight line, zeta 0.45. This is the damping ratio line, brother. So this damping ratio line will intersect with the root locus at minus 1.5 plus J3. That is your dominant pole. Okay?
Yeah.
Hmm.
Thank you. Shukran.
Okay. Have fun, Habibi. Have fun. Okay, PI controller is given. Given. Okay? Given meaning that you don't have to choose lah. 0.1 or 0.01 or 0.001. Everybody use the same GPI. Okay? Follow as written there. So, form the transfer function of GS, GPI, and determine the value of gain K. Given GPI is S plus 0.01 over S, correct? See, G is equal to K S plus 7 S square plus 4S plus 8. Can? So GPI multiplied by G. So you will get K S plus 0.01 over S plus 7 S square 4S plus 8. Correct? Correct, guys?
Ya, Doktor.
Alright, Doctor.
Benar.
How to find K, the gain, the new gain?
Magnitude.
Lah, magnitude tu macam mana? Amir Farhan. S plus 7.
Yes, Doctor.
Huh? Magnitude.
Magnitude over zeros.
Minus 0.01. Okay. And the value is the just now that you get plus J3 kan? You insert inside.
Yeah.
Then you will get the K equal to
36.1.
36.1. Huh? 36.1? Okay lah, 36.1. 36.1 Okay, 36.1. Compute the steady state error for the compensator system with PI controller. Then compare the result to the answer in Q2B and provide a brief explanation. Okay, previous steady state error berapa? Previous was 0.61 0.61 kan? Aina, yang you kira tadi. Current ESS tak tahu. So we have to calculate KP. Limit S to 0 kan? K S plus 0.01 over S plus 7 S square plus 4S plus 8, correct? Correct, eh? So this one is 36.1. Kan? So replace with 0, 36.1 multiplied by 0.01. 0 multiplied 7 multiplied 8. Apa? Dylan? Dylan. Dylan. Tak datang. GN. GN. GN pun tak datang.
Can you hear me?
Yeah.
Infinity.
Infinity. And the steady state error now become?
0.
0.
Zero.
0, eh? So the previous one was 0.61. Now the steady state error has been reduced to 0 due to the PI controller. And the response maintained as the same transient response. Okay. Has been reduced from to 0, but transient response maintained. Status quo. Status quo meaning no change. Okay. So what is the next question? Next question. Okay. Determine the values of Kp, Ki of the PI controller. All right. GPI is equal to Ks plus Z over S, which is GPI 36.1 S plus 0.01 over S. And this one is GPI Kp S plus Ki over Kp equal to S. So you compare. Can you compare this? Can you compare? Shazwina, are you there? Shazwina. Rahman? Rahman.
Ya, doktor.
KP berapa?
Oh, Syahman, doktor.
Rahman.
36.1.
6 point. KI? KI berapa? Rahman, KI berapa? Rahman?
0.361.
0.361. So this value, KP 6.1 and KI 0.361 will be inserted inside the controller, okay, using potentiometer or attenuator, variable resistance, or you just insert the values. If it's a digital controller, you just insert the value KP 36.1 and KI 0.361. If you don't have digital controller, you have analog controller, so you have to tune the variable resistor so that the gain is 36.1 for KP and KI 0.361. Understand? Understand or not?
I understand.
You have class after 12? Ada kelas tak? Do you have this class after 12? Pukul 12 ada kelas?
No, doctor.
Okay, those who have class, you can quit from the room. Okay, and those who don't have class, stay in the class because I will finish until 1 p.m. to do the revisions, recorded, and then share with others. Those who have class at 12 may exit, and you can see the remaining of the recorded revision lecture by YouTube. Okay, do you understand?
Yes, doctor. Thank you.
So I will continue with next question, which is the semester 1, 23-24. Okay. 23-24, which is a test 1. So, Akil, you're the class ke? Pukul 12? Akil? Irfan, you're the class ke? Pukul 12? Okay, we continue. For question 1, where you are given unity feedback transfer functions. Okay, s plus 3, s squared plus 2s plus 2. Then this is a root locus questions, chapter 1. Find the asymptote real axis intercept and angles of asymptotes. Then the point where the root locus intersects the imaginary axis and the gain value at the intersection point. The breakaway point, the departure angle, and sketch the root locus of the system. So this is the third order system. And system type 1. Okay. So find the intercept of the real axis. This one is known as sigma A. And the angles of asymptote, theta A. Okay. So is there any plot given? Okay, no plot given. So by using a formula, okay, sigma A is the value of the poles divided by the number of poles. Okay, so it should be 0 plus minus 3 plus the values minus 1 and minus 1. Okay, divide by 4. Okay, so if you look here, this one is minus 1 plus j1. So minus 1 plus minus j1. So when you add these two poles, the imaginary will cancel out. That's why you get minus 1 and minus 1. Okay, so the sigma A is minus 1.25. Okay, and then the angle of asymptotes is 2k plus 1 divided by pi, 2k plus 1 pi, divide number of asymptotes, okay, which is 4. So you will get theta A is 45 degrees, 135 degrees, 225 degrees, and 305 degrees. Okay. This one is for k equal to 0, 1, 2, and 3. Okay, where you use this insert inside the key. Then find the point of the root locus intersects the imaginary axis and the gain value at that point. Okay, so this one is done. So this one you have to find the j omega and the gain k. Okay, so ds is equal to k s plus 3 s squared plus 2s plus 2 open loop closed loop transfer function is k okay, and the characteristic equation s plus 3 plus k equal to 0. Okay, Simplified, s power of 4 plus s square cubic 8 s square plus 6s plus k equal to 0. Okay. Then use root width. Insert the coefficient of characteristic equation into root width table. So you will get s power 4, s power 3. Okay, 1, 5, 8, 6, k 0. Then you have to fill up this s square, s1 and s0. Okay, so this one will be 6.8. This one will be k0. Okay. So at this point, there is a row of zeros happening here. Okay. The whole s power of 1 is row of zeros. So you need to somehow adjust, okay, row of zeros, which is 40.8.5k equal to 0, k is equal to 8.16. And then develop the equation PS 68 s squared plus k equal to 0. Okay. Then you find that s is equal to plus minus j 1.1. So you can see that the j omega crossing root locus at plus minus j 1.1. Okay. And the gain values k critical because at j omega is over s plus 3, s square plus 2s plus 2. Okay, so use plus j 1.1 insert inside, then you will find the k critical at 8.16. Okay, root locus plot is not given. Okay, that's why you have to calculate. Okay, cannot observe. So we cannot read from that. Okay. Next is the breakaway point. Also, breakaway point we have to calculate. Okay. Breakaway point by using differentiation. Okay. d per ds, open loop transfer function, which is d per ds gs equal to 0. So you calculate equal to 0. Okay. Then you will find s, solve for s, minus 2.29 minus 0.7 plus minus j 0.35. So which one to choose? We choose the real number, which is minus 2.29, or S equal to minus 2.3. Okay, this one. This one, don't choose. Departure angles, as usual, use the formula for departure angle, theta departure. Okay, angle criteria. Which is the theta departure equal to summations angles of zeros minus summation angles of poles. Okay, so theta d is equal to plus 180 degrees. Don't forget that. Okay, so it's minus 71.6 degrees and plus 71.6 degrees. Okay, so if we see the plot, okay, of the root locus, we have over here 0. We have over here how much? 3. And then plus minus J1. Okay. So how many branch of root locus? We have 4 branch. Okay. One is this color, infinity. Second one is this one, infinity. Okay. This one is, third one is okay, infinity. And the green one is something like this, to infinity. Okay. So you can see that the theta departure is over here, theta departure, and the other one is over here, the conjugate theta departure as well. Okay, for the second root locus and for the first root locus. Over here. Okay, sketch the root locus. Question 2. Okay. Aina, Shakira, are you there? Aina, Shakira, are you there?
Yes, Doctor.
Can you read the question for me?
A unity feedback system as shown in figure Q.2 has a forward transfer function GS equal to S square minus 4S plus 20 over S square plus 8S plus 12. The system is required to operate at a percentage overshoot of 10%. The root locus of the system is shown in figure Q.2 angka Roman 2. A. Determine the exact point S K and gain K where the root locus crosses the damping ratio line at 10% overshoot. B. From the root locus, find the stability range of gain K for the system. C. Compute the steady state error for the system using a unity step input. D. Using a proportional integral PI controller, GPI is equal to KS plus 0.01 over S. Determine the overall compensated system. Next, prove that the steady state error of the compensated system is eliminated when applied with the PI controller using the same input as in C. The the general transfer function of the PI controller is also written as GPI as equal to KP plus KT over S. Determine the value of KP and KI.
Thank you very much. Okay, so these questions, root locus is given, eh? Okay, can see the root locus there. Okay, so we see that the complex conjugate zeros there is 2 plus J4, all right? This one is 2 minus J4, all right? And followed by -2 and -6. Okay. This is a second order system. And system type 1 or type 0. What is it? Type 1 or type 0?
Type
Huh?
type 0.
Type 0. Betul. Type 0.
InsyaAllah.
Tembak je. Tak tahu. Right. Apa dia punya open loopholes? Open loopholes. -2, -6. Open loop zeros. Okay. Overshoot percentage 10%. Okay. So if 10%, overshoot 10%, what is the value of zeta from the graph? Amir Farhan?
Yes, Doctor.
Zeta bila overshoot 10%.
0.58.
0.6 lah. Okay.
0.6.
Okay. Setuju? Okay. 0.6. So 0.6 will give theta Danish Kayib. 0.6 will give theta
3.13.
huh?
53.13.
53.13. Okay. So we draw lah 53.13 using the tu lebih kurang dekat sini. Kat situ lebih kurang. Okay, nampak eh? So pakai ruler. Okay. So this is zeta 0.6, which will give you theta, this one, 53.13. And what is the dominant pole over there? Ahmad Yosef.
Uh, negative 2.24 plus J3.
Plus minus J 3.0. And the corresponding gain?
Gain poles over zeros.
Okay, formula?
S square plus LS plus 12 over magnitude of S square minus 4S plus 20.
And replace with the value.
Dominant pole.
So you will get K roughly 0.416. Okay. Okay. From the rule occurs, find the stability range of gain K for the system. So how to find the stability range? Iza, how to find the stability range? Iza Shamimi. Tak ada, tak datang. Aulia?
Kena tengok range K kan apa?
Stability range.
Ha? Apa dia tu?
Stability range.
Kena tengok range K kan?
Tengok kat sini, berapa ni? Tu
So,
berapa ni? Cross tu, J omega crossing berapa?
sekejap, tengok mana boleh?
Tengok kau punya iPad.
Alamak. Saya, sekejap. Ya.
4.16. Lebih kurang. J 4.16. Sini. J 4.16. Nampak tak yang saya tulis ni? Nampak kan?
Nampak. Nampak.
Nanti tak faham tengok balik.
Boleh.
So, what is the gain K over there? K critical. S square minus 4S plus 20. Kan? So insert S plus J 4.16. Insert inside here. Then you get the K critical.
2.008 tu lah tu.
Hmm?
Is it 2.008?
Dua lah. Okay.
Dua.
By range of K for stability is
022. Is it?
okay. 0 to 2. Kan? Then we use the next question is steady state error for the system unit input. Okay. Steady state error. Senang je. System type apa? Type 0 kan? System type 0. use KP. KP sama dengan KGS. Okay. K berapa? What is the value of K? Guys, K is 0.416. Okay. S square over S square. Okay. Zero point 69. Can. So the steady state error equal to 0.59. So use the PI controller here. Oh, macam tadi. Okay. Using a integral, determine the overall compensated system. Okay, same. Next, prove that the steady state error of the compensated system is eliminated when apply the PI controller using the input. Okay. So we just multiply je lah. Okay. Tak cukup ruang. So kita pindah sini. Okay. G overall. GPI multiplied by G. Okay. K over S okay. So this is the G overall. And this one is 0.416 at the particular zeta that we mentioned. Okay. So KP. Now you have to calculate for the KP. Okay. Which is a 0.416. Okay. So you replace KP, so it will become infinity. Then the error is 1 over infinity equal to 0. Okay. And finally, the general transformation of PI controller is shown is okay. Macam tadi, okay, determine the KP and KI, right? This is very important because you need to find the KP value and KI value to be inserted inside the hardware or inside the software of the computer for digital PI controller. Okay. So we start with GPI standard form that we get over S. Okay. And this is known as KP plus KI over S. And can be factorized as KP S plus Ki over Kp, okay, over S. So straight away, you compare. Aina, can you help me? Compare Kp equal to 0.416. Kan? Ki is equal to Kp sama dengan 0.01. That's why Ki is equal to 0.01 multiplied Kp, which is 0.416, which is 0.0416 multiplied by 10 power of minus 3. So that's how we calculate the Ki values. Okay, guys? Okay, I think we stop here. Okay, we will continue again to discuss another set in the Thursday class. Thank you very much for your attentions. Okay, see you later on Thursday. Thank you. Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Shukran.
Thank you, Doctor.
Thank you, Doctor.
I will share the recorded later, by today.
Okay, Doctor.